Welcome back to another power series. We are going to find the interval of convergence and radius of convergence. So we have a given power series, and this one we will use the ratio test. So for the time, to save us some time, I already give you the an and the an plus 1. So the an is the original series. The an, you have to replace the n with n plus 1. And other than that, we have to simplify the exponent a little bit in order to make the simplification more convenient. So for the limit, we have to set up a ratio between the an plus 1 and an. So there is a minor mistake. The top should be an plus 1. The bottom is supposed to be an. And then you go ahead and then do the an plus 1. So that means you copy the n plus 1 again. So n plus 1, x to the n, x to the first, divided by 2n, 2 to the first, and then n squared plus 2n plus 2. How come there is a big difference between this and the an? If you look at the first line of an plus 1, do you see that inside the parenthesis we have another parenthesis? We have to replace the n with n plus 1. So the n plus 1 square, you have to expand that. So n plus 1 square is equals to n squared plus 2n plus 1, right? So you have a 1 plus 1. That's how you end up with a 2. So you can, it's not too difficult for a calculus student. And then multiply the reciprocal of an. So we have a n and then xn in the denominator, and then 2n, and then n squared plus 1 on top. Do some simplification. So first of all, I see that the 2n will be gone, and then the xn will be gone. I think that's all. All right, and then you have an n plus 1 and an n squared plus 1 on top. I would like you to fully expand that. Can you do that in one step? That is equals to, I will just give you n to the third plus n squared plus n plus 1, and then the denominator, you don't need to expand anything. That's make a distribution, n to the third plus 2n squared plus 2n. How do you deal with this? And then other than that, we have a x divided by 2, right? So what is the highest degree in the denominator? The highest degree is 3. I don't care the numerator. So that's why you have to divide each term by n to the third. I don't care about the numerator. So even though you have the numerator, the biggest degree is 1,000 or 1,000,000 or a 1, I still divide each term by x to the third. The third came from the highest degree in the denominator. The reason I only take care of the denominator is I cannot allow a 0 in the denominator. That's the reason. And you learned this when you were learning limit, the first lesson of limit back to differential calculus. Okay, do the math. So the top, you have limit as n approaches to infinity. You have 1 plus 1 divided by n squared plus 1 divided by, no, that is just an n, but it will be 0 anyway. N squared plus 1 divided by n to the third divided by 1 plus 2 divided by n plus 2 divided by n squared, all the fractions become 0, times x divided by 2. So you have a 1 times absolute value of x divided by 2, right? The 2 is always positive. You don't need to wrap the 2 by absolute value. That must be less than 1. Why less than 1? I like to explain this. So this is less than 1 due to the geometric series. So the geometric series, you have a common ratio r raised to the nth power. In order for the geometric series to be convergent, we must have the absolute value of the common ratio less than 1. So in this power series, do you see that there is an x to the n? So if you look at the green circle itself, that is actually a geometric series, and then the base, which is the common ratio, is x. So that's why we must take the absolute value of x less than 1 in order to make the series convergent. So to make the series convergent, and then you have to solve this inequality. You multiply both sides by 1. Absolute value of x is less than 2, so that is negative 2 less than x less than 2, and then you have to test the 2n, right? So when x is equals to 2, when x is equals to 2, you plug in the 2 to a power series, then you have summation, n goes from 1 to infinity, n divided by 2 to the n. This is what the series gives us, right? And then instead of x to the n, you do a 2 to the n, and then you can see that this 2 to the n and this 2 to the n will be cancelled. You always get convenient stuff like that when you do the testing. N equals to 1 to infinity, you have n divided by n squared plus 1. And then how do we do this? So to do this one, we have to use a limit comparison test. So use limit comparison test, and then we have an equals to n divided by n squared plus 1, and then bn is equals to n divided by n squared, no plus 1, because when n is so big, the plus 1 makes no difference. And then that is n, and then this is a harmonic series, and it's always converge. And then what else do we do? We compare the ratio, right? So limit as n approaches to infinity, an divided by bn. I believe the reason I use a limit comparison test, if you use just a general comparison test, that doesn't give you a conclusion. You can try, that won't give you a conclusion. So that's why I just do the limit comparison test. And then you have a limit as n approaches to infinity. You have n divided by n squared plus 1, and then 1 divided by n is n divided by 1. So you have a limit as n approaches to infinity, n squared divided by n squared plus 1, and then you do the same trick. The highest degree is 2, so you divide each term by n squared. So at the end of the day, what do you have? You have limit as n approaches to infinity, 1 plus 1 divided by n squared, so that will be just a 1. So this one is greater than 0. So what does that mean? That means by limit comparison test, the series diverges, right? So the series diverges when x is equals to 2. So diverges when x is equals to 2 by limit comparison test. So that is the right endpoint. And then the left endpoint, let's switch color. So when x is equals to -2, x is equals to -2, oh, that gives you an alternating series then. Some people like this, some people hate this. And then n goes from 1 to infinity, n to n, and then n squared plus 1. You have -2 to the n. And then what I am going to do next is I want to break down the -2 to the n to a -1 to the n times 2 to the n, because there is a 2 to the n in the denominator. And yes, you're right, this is a technique that you will have to learn in this lesson. From 1 to infinity, you have a n divided by 2n, n squared plus 1, and this is a 2n, and then -1 to the n, and then I can make a simplification before analyzing the alternating series. And then what is my bn? My bn is the everything else without the alternating term, and then the bn plus 1 is n plus 1 divided by, you square that, then that will be n. Actually, we don't need to expand this. And then number 1, you have to prove that the bn plus 1 is less than or equal to bn. So when n is equals to 1, we have 2. 2 squared is 4, 4 plus 1 is 5, less than or equal to 1 divided by 2. Yup, 0.5 is greater than that. 0.5 is greater than or equal to 0.4. And then number 1 is satisfied. And then number 2, you have limit as n approaches to infinity of bn, that is n divided by n squared plus 1. So we decide the highest degree in the denominator is 2. Then we do that, divide each term by n squared. So we have the limit as n approaches to infinity, 1 divided by n, 1 plus 1 divided by n squared. So as n approaches to infinity, that is 0. So number 1 and 2 are satisfied. Then the limit is converged when x is equals to -2 using alternating series test. So we have a diverge and a converge. Here is how we sum up the conclusion. We draw a number line. This number line represents x, and then we have a -2, and then we have a 2. So -2 is converged, then we use a solid circle, and then 2 is diverged, then we use an open circle, right? Yep. So between -2 and 2, the series is converged outside of the interval or diverge. So the interval of convergence, using interval notation, is between -2 and 2, using inequality that is between -2 less than or equal to x less than 2. And then a 0 is right in the middle, and then the radius of convergence is equals to 2. All right, so that is the end of this video. A lot of work. That's why I want to put this video in. I want to put this problem in one individual video. What do you think? Good? Did I help you to solve this problem? I am sure the answer is yes. Let me know in the comment section below. As always, a thank you would be nice. Like the video, subscribe to my channel. Appreciate your help. I will see you all in the next lesson. In the next lesson, I will solve another power series. All right, I see you all in there.